Good morning, dear students. Let us start module 3, first part, that is time response of feedback control system of first order systems. Okay, what is what is actually the time response? Time response is the response of a dynamic system for the applied input. Okay, we will be expressing this response as a function of time. Okay, so we can say that in time domain analysis, the response of the dynamic system to an input is expressed as a function of time. It is possible to calculate the what we call output time response if the mathematical model is available. Okay, so if it is not available, then it's very difficult because we have to compute the what we call system behavior. Then we have to apply the input and we have to compute the output response as a function of time. So if mathematical model is available, it is very easy to compute the output response, which is as a function of time for the applied input. Usually input will not be easily known or easily available what we call ahead of time. So we say that input signal to a control system are not known fully ahead of time. Say for example, in a what we call radar tracking system, or it may be a weather forecasting system. See, we will not be knowing what sort of input we will be getting. It will be keep changing. Okay, so we have here an example in a radar tracking system. The position and the speed of the target to be tracked may vary in a random fashion. So it is very difficult to model an input signal mathematically by a simple equations. So it is very, very tough to predict the input or to model the input. So here for the design purpose, we will be using the standard test signals, which almost covers the all possible characteristics of the actual input signal which can occur naturally. So naturally, we can expect a sudden shock or a sudden change, a constant velocity or a constant acceleration. So we are going to model these characteristics, and we used to have standard test signals available. So we can take for a sudden shock, we can take a impulse input. For a sudden change, we can take a step input, and we have a constant velocity, a ramp input, and we have a constant acceleration, we can have a parabolic input. So we can have these standard test signals used for these standard possible characteristics of input which can occur in a control system. So another standard signal we have, that is a sinusoidal signal. Sometimes, we encounter such input signal. So we will be using that also as a standard test signal. Okay. To start with, we have we'll start with the first test signal, that is impulse. Okay. So the impulse signal imitate the sudden shock characteristics of actual input signal, as we have discussed before. Mathematically, we can represent an impulse input. So we use delta of t as a name, or to represent an impulse. So it can have a value a for time t is equal to 0, and it will be 0 for all other time. So this is a graphical representation of an impulse. You can see here graphically, at t is equal to 0, you have an impulse a existing, and all other time, you will find no signal existing here. So this is what the definition of an impulse. So if the value of a found to be 1, then the impulse is called a unit impulse signal. Second one, we have a step signal. So step signal imitate the sudden change characteristics of actual input signal. Sudden change, you can see graphically here. See, at time t is equal to 0, there is a sudden change happening from level 0 to level a, and that remains constant for all the time t greater than or equal to 0. So we define a step signal mathematically this way. We represent step signal with u of t. The name here, we always use it as a u of t, which represent a step signal which is equal to a for all the time t greater than or equal to 0, and u of t will be 0 for t less than 0. That is what here graphically visible. You can see that for negative time it is 0, for positive time, that is for t 0 and greater than 0, you have a constant signal here a. So that is what the characteristics of a step signal. So if a value found to be 1, then we call that as a unit step signal. So next we have a ramp signal. Ramp signal imitates the constant velocity characteristics of input signal. You can see here constant velocity, constantly changing signal. You can see, for t0, 0 or greater than 0, you will find that the signal constantly, signal is having constant velocity here. And for t less than 0, it is 0. So that is what here mathematically we are representing it. The ramp signal we will be representing with R of t, which is equal to A of t for t greater than or equal to 0, and it is equal to 0 for t less than 0. So as similar to the previous cases, if A found to be 1, we'll find the signal unit ramp signal. The signal will be called as unit ramp signal. You can see here the ramp signals with a slope A. That is, whenever time is equal to 1, you will be having output as A, and if time becomes 2, you will find it as 2A. That is what the equation here says. So if time is equal to 3, you will be having 3A. So this is what we have, a ramp signal with a slope A. And similarly, I can have a unity slope possible. That is, for time 1, you will find that the output also 1. For time 2, output is also 2. This is what we have, a unit ramp signal. This is how we represent a ramp signal. This is a ramp signal with a slope A. This is a general ramp signal representation which mimic or which imitates the constant velocity characteristics. Similarly, we have a parabolic signal which imitates the constant acceleration characteristic. So we can represent mathematically the parabolic signal P of t equals at square divided by 2 for t greater than or equal to 0, and it is 0 for all the time t less than 0. This is what the graphical representation of a parabolic signal. You can see that it varies in a parabolic fashion. So if a value found to be 1, then the signal is said to be a unit parabolic signal. So here again we have an example that is for a parabolic signal with a slope a. That means for time t is equal to 1, you have 0.5a. How can I say that? Just refer the equation here. That is a into t square by 2. So if you substitute 1, if you t substitute 1, then you will be having 0.5a. You will be having here the value becoming 0.5a. So that's what we have taken here. Similarly, if you substitute t is equal to 2, what you will get in the equation? Substitute t is equal to 2, then it is 2 square. You will be having 4. 4 divided by 2, it is 2. So totally you will be having 2a. So 2a we have here. So you will get a graph here. You will get a pattern or you will get a parabolic shape. We call this as a slope a. Okay, this is a graph with a slope a. Similarly, I can have a unit slope here. That is a can become 1. So if a becomes 1, you will be having only t square by 2 equation to be imagined here. So it is for 1, you will be having 0.5. For 2, you will be having 2. For 3, you will be having 4.5. So all the values are same. Only thing is a becoming 1. So you will get it as a unit parabolic signal. Now, how these test signals are interrelated. So we already we have learned in the beginning first module classes, we have learned that impulse response, or sorry, impulse signal, if you integrate, you will get step. If you integrate step, you will get ramp. If you integrate ramp, you will get parabolic signal. The other way, if you go, if you differentiate parabolic signal, you will get ramp. If you differentiate ramp, you will get step. If you differentiate step, you will get impulse. Okay, so they are highly related here. You can say that if you have impulse, you can create step by just integrating that. So if you're having a impulse response, then you can simply integrate that to get a step response. Similarly, if you have a step response with you, you can simply differentiate and you can see that how a response will look like for an impulse input, because all the inputs here we have standard input signal, they are highly connected. So one response you have, the other one you can construct. because they are related in this fashion. So now we have to understand the standard Laplace transformation of these signals, because it's very much important, because without Laplace transformation we cannot have a transfer function design. So transfer function is very essential here to analyze the what we call time domain response or time response of a control system. So for impulse, we have delta t representation, mathematical representation of an impulse we have already seen. So Laplace transformation of this impulse delta s, which will be a, simply a. Okay, so what is the Laplace transformation of a step? So we have seen the mathematical model of a step signal, and if you take a Laplace transform of that, it will be u of s, which will be a divided by s. Similarly, for a ramp, you have a divided by s square. For parabolic, you have 2a divided by s cube. So these are all the standard test signal and its Laplace transformation. Why it is important? For constructing a transfer function, it is very important. I want input to be in Laplace domain, so that I'll be getting output also in the Laplace domain, so that inverse Laplace I can take so as to get the time domain response. Okay. So as we know that time response of a dynamic system response is expressed as a function of time for the applied input. So we can we can express, or we can pictorially represent it as, if you have a system, you have to apply a standard test signal, you get an output here. That output, if you plot with respect to time, you call that as a time response of this dynamic system. Okay, so this is what we call it as a time response of a dynamic system. So the time response of any system here will be having two components. One is transient and another one is steady state. Okay, what is transient response? Transient response is the time taken by a system to settle down, time taken by a system to settle down if it is disturbed or if it is changed. I repeat, the time taken by the response of the system to settle down if it is changed from its rest or an equilibrium position. Okay, so transient response is a response of a system from rest to equilibrium or a steady state, we call it as. Okay, so now what is steady state? So steady state is the response of the system after transient response is died out. Okay, once the transient gets over, then it is a steady state response. Okay, so for example, here step input has been applied, then you can see that suddenly you will not get the steady state appears at the output. It takes time to reach that final value, or what we call it as steady value. So the time taken by a system to reach its steady value is what we call it as a transient time or a transient response. And once it reached a fixed or a constant value, once it settled down, then it is a steady state. We call it as a steady state. So whenever we analyze the time response of a system, we will be having these two major parts, that is transient and steady state. Both are very important. You can see that the behavior here, it is totally different, and see the behavior at the steady state, it is different. Okay, together gives us the time response of a system. Okay, so this is what we call it as. Now we have to observe here that the transient response depends on only the characteristic equation of the system, not the input. I repeat, the transient response depends on only the characteristic equation. In the characteristic equation, whatever roots we get, we call it as poles of the system. The poles and poles position will define the transient behavior of the system. So input is not having any effect here for the transient section. Okay, So therefore, if you study transient response for one standard input, it's sufficient. You need not change the input and study the transient. Transient remains same for all the input, because transient response depends on the system characteristic equation. That is the number of poles and poles position will decide the transient pattern. So for one input, if you analyze transient, it is sufficient. You need not change the input and study the transient section. Whereas steady state, it is not like that. Steady state response depends on the system dynamics, that is the system parameters and the input quantity. Okay, so for the steady state, you have to examine using different test signals. That is for for example, if you are changing the input, you will see that the output steady state will change. So that we apply a final value theorem, and we'll try to estimate what could be the steady state value of that particular for that particular input. Okay, we use a final value theorem. In a Laplace transform, we have a final value theorem. We apply that, and we'll see what is the possible final value that a signal can attain. So we'll take here a very simple first order system which has got only one pole. Okay, so we have got only one pole, a simple first order system we will be taking here. So C of S by R of S is equal to K divided by T into S plus 1, where K represent the gain, that is DC gain, and T represent the time constant. What is the time constant? Time constant is the it's estimation which tells us how quickly the system attains the final value, how quickly the output rises, or how quickly the output can attain a steady state. That is what this capital T we have, that is time constant, will give. The gain is what the gain will be getting, that is the steady state value divided by the input. What is K? It is a steady state value divided by the input, is what we call it as a DC gain, and T is how quickly the system will attain the final value. That is how quickly the first order system respond to the unit step input, is what the time constant gives us. Okay, and as I said, DC gain of the system is the ratio between input signal and the steady state value of the output. Okay, so that ratio will give us the gain. So now we have a first order system, G of S, which is equal to 10 divided by 3S plus 1. So according to the formula, it is very clear that the gain is 10 and the time constant is 3. Okay, we have one more representation of a transfer function here, G of S, which is equal to 3 divided by S plus 5. Now I cannot tell here exactly what is the gain and what is the time constant. What I should do, I should get it back to the standard pattern. What is the standard pattern? I should have in the numerator only one constant, and in the denominator I should have coefficient for S, which is the time constant, plus I should have a unity value here. Okay, so how to make this unity? I'll divide numerator and the denominator by 5. If I do that, I will get a unity at this position. 1 I'll get here. So I have now the standard pattern, that is G of S is equal to K divided by capital T into S plus 1. Then this is what 3 by 5 is what the DC gain we can call it as, and 1 by 5 I call it as a time constant. Okay, now consider the first order system. Let us find the impulse response of it. Okay, so now this is how an impulse looks like, as we have seen in the previous slides. This is how we represent an impulse. At t is equal to 0, you have a signal 1, and in all other time you will find no signal. That is what a impulse definition. Let us apply input here, an impulse, and we'll see what is the output. Okay, so what is the Laplace transformation of an impulse? Again, this we have discussed. Laplace transformation of an impulse is 1. Okay, since it is 1, what is the output? I can say output is equal to input multiplied by the system transfer function. Since this is the system transfer function multiplied by the input, is what the output. Okay, since output is in Laplace transform domain, and this system representation is in Laplace domain, I have to keep input in Laplace. So I have taken input in the Laplace transform domain, and I found that impulse will become 1 in Laplace domain. So 1 multiplied by this transfer function is what the output C of S. That is what we have written. Okay, so in short, what I can say, the impulse response is the transfer function given. Okay, whatever transfer function given, it is the impulse response of the system itself. Okay, so that's what we wanted to conclude. So now we will take that transfer function, which is also called as impulse response, and I'll try to do some term adjustment. Why do I do that? Because it is easy for me to take the inverse Laplace. Okay, so as to take the inverse Laplace comfortably, I'm doing some term adjustment. What I did, I divide numerator and denominator by t, I get an expression like this. So we have according to the inverse Laplace transformation procedure, what is the inverse Laplace of C divided by S plus A? It is equal to capital C into e power minus AT. Compare this with the transfer function what we have. By comparing, I can say that capital C is K divided by T, and here the small a is 1 by T. So what I can write? So C of T, I can write it as capital K divided by capital T. That is what we have, time constant, and capital K is the DC gain, into e power minus small t by capital T. Okay, so this is what we can write as the C of T. So this C of T is called the time response of the given first order system for the impulse input. Okay, so I can say that in short, it is an impulse response of a first order system. I repeat, this is an impulse response of a first order system. Now let us analyze this expression. So I will take k value 3 and I will take t value 2. Okay, how a graph look like? So the time response I have plotted here because I got an equation. Now for this equation, I have assumed the constant k as 3 and I assumed the capital T, that is time constant, as 2. Then how a graph look like? For the given equation, you substitute k is equal to 3 and t is equal to 2 if you substitute. And you can find here what? You can find here e power minus t divided by t. Okay, so if you substitute here for capital T2, okay, then for time t is equal to 0, you will find 1.5. Correct, because small t, if you make it 0, this exponential term will become 1, and k divided by t is the 3 divided by 2, which is 1.5. So I'm starting at 1.5, and as time increases, you will find that the value decreases and decreases. Okay, that is what we have. So as time increases, you will find the value decreases. You can substitute and see. You can randomly substitute some value for t here because capital T is fixed. The small t is what the time representation. You can change the values of small t and you can see how the values will be dropping and how it will take the shape. You can randomly substitute some values for small t and you can see standard values I have just noted down here, 2, 4, 6, 8. You can substitute and you can calculate what is that C of t, and if you join all the points, you will get this curve. Okay. So now step input I'll take. Okay, we will see how a system behaves for a step input, or I can say that step response of a first order system. Okay, so now what is the Laplace transformation of a step? It is 1 by S. What is a first order system representation? First order system representation with one pole, we have K divided by capital T S plus 1. This is what the first order system representation, and this is what the output, and this is what the input R of S, and now the R of S I am applying a step, that is 1 by S. So what is the output? Output is equal to C of S, which is equal to input multiplied by the transfer function is what the output we have. So that's what we have done. It is K divided by S into TS plus 1. So now how to continue from this point? Once we are ready with the transfer function, calculating the time response is very simple. We have to take simply the inverse Laplace. So we will move from that complex frequency domain back to time domain, and we can get a response, time response, we will get it. Okay. So now, how to take it. I have to split this into partial fraction, and I have to take a inverse Laplace. That is very easy method. So I'll go with the partial fraction method, and I'll try to split this ratio into two, and I'll be having a two constant a and b, found it as k and minus kt, and I have substituted here. So I got now the two term. The first term I call it as a forced response. That means output I am getting because of the input applied. Okay. So second one is natural response. What is natural response? That is the amount of output I am getting due to the transfer function characteristics or the system functionality, like that. So you will be having a forced response and a natural response. Natural response is what the impulse response we have, that is a pure system behavior we call it as. And the first term what we have is the term we got due to the application of the input, so I call it as a forced response. So we have forced step input, so because of that we are getting that term in the output response. This is what we call it as a natural response, that is due to the system transfer function. So this is what we got it. K has been taken out as a common, and we are taking inverse Laplace. So 1 by s represent a step. I have taken u of t here. T divided by ts plus 1. This term adjustment I have done it. T I'll be taking to the right. So I'll be having here 1 by t divided by s plus 1 by t. So I can take that as e power minus t by t, capital T. So this is what the inverse Laplace, of the first order step response equation. So, I know that, I'm dealing with the unity step input. So I'll make u of t 1. Okay. If I make u of t 1, and when time t becomes capital T, okay, when time t is equal to the time constant, then you will get that the output response will be reaching 63% of its final value. Okay, output response will be reaching 63.2% of its output value. So how did I get to know that? I have just substituted in the equation. I made small t taking the capital T value, that is time constant value. At that situation, what's happening? I will find that the output reaches the 63% of its final value. Okay, so that's what we have here, a graph. So this is a graph showing the step response of a first order system, and here we have k is equal to 10, and capital T is equal to 1.5. We have 1.5 seconds we have. So this is what the CFT expression, time response equation we have. So we have plotted for different t values, different time values we have plotted. Okay, and we know that the k value is 10 and unit step is applied. Okay, so the final value can be at most 10. Okay, that's what the inference we can say. The steady state value or the final value can be 10 because k is equal to 10 and input is a unity step input. Okay, so now here I'll go to a salient point, that is exactly at 1.5 millisecond, which is a time constant. Exactly at 1.5, if you go, you will find that the output has reached 63.2%. approximately 63%. So it has reached the 63%. So this is what one information we should have it. That is, in a first order step response, if you take it. So at time constant t, what you will find, the output will be reaching to its 63% value. Okay. So, gradually after a few more time lapse, you will find that it is reaching the steady state. But exactly at the time constant t, it will be reaching 63%. Next, again we are analyzing step response here for a different time constant. Different time constant. The same equation I have here, that is first order step time response equation I have. So I'm having the K, that is gain fixed. Gain I'm not changing, which is 10, and only the time constant I'm changing. So how a graph look like? You can see a blue color line. You can see that the rise in the output is very fast because the time constant is smaller value. As the time constant becomes bigger, you could see that it is taking much time to reach its the final value, or it's very slow. It is not at all quick in picking up the values. It is taking much time to pick up the values. That is what the slide explains here. So time constant is giving us the information how quick the system is in picking up the output values. So first one, time constant 1, if you operate, you will see that the output rises very fast, whereas for the time constant with a higher value, it rises very slow. Okay, so we have 5 major points here in the response, or major time points, or major time observation points, we call it as. One is for time t is equal to capital T, that is when time t is equal to the time constant, I could see that it is reaching, output is reaching 63.2%. When time t reaches twice the time constant, it is 86.5. So if time reaches thrice the time constant, it is 95%. If it reaches 4 times the time constant, then the output will be reaching to 98.2%. Similarly, if it reaches 5t, then it is 99.3%. This is what the major observation we do it. Only thing is you have to substitute in the equation the small t value. You will get to know what are the different percentage of output available at so many time instants. So for T 63.2, for 2T it is 86.5, for 3T 95, 4T it is 98.2, and for 5T it will be attaining 99.3%. Same step response of the first order we are talking about here. We don't disturb the time constant T. We disturb what? We disturb the gain of the system. You can see the graph here. By changing the gain, the pattern or the graph shape is not changing. The shape is ideal for k is equal to 10, k is equal to 4, k is equal to 3, k is equal to 1. Only thing is the height is different. That amplitude is changing here. So for gain 10, you have a higher amplitude here, and for k5 you will be having lower, or for k is equal to 1 you will be having much lower. Okay, so the output height, you will find less, the strength will be less, but the characteristics or shape will not change as the gain changes. Okay, so this is what you have to observe. Only the amplitude here changing as the time changes. Okay, so now relationship between the step and the impulse response we have to understand. Okay, as I said, step and impulse are related, because if I integrate impulse, I'll get step. If I differentiate step, I'll be getting impulse. So this relation we already aware. Now we will take up a step response of a first order system. Okay, step response of a first order system, we have like this. You have to simply differentiate this. You have to simply differentiate, you will get a impulse response. Okay, you are differentiating this, you will get a impulse response. Okay, so you have to simply differentiate to get the impulse response. Okay, so I'll stop here. I'll continue with this in the next class. Okay, so examples on this first order system, I'll just continue in the next class. Thank you.